We're going to be doing credit card fraud detection, so it is important that credit card companies are able to recognize fraudulent credit card transactions. That's what our machine learning model is going to try and do, so that customers are not charged for items that they did not purchase. Now, the data set has a lot of information. We have 284,807 transactions, which are either fraud or not fraud, but only 492 of them are fraud. We can obviously think that most transactions are not going to be fraudulent, and so only 0.172% of them are positive class. We'll make the positive class fraudulent because it's basically we're flagging, trying to say, hey, this is a fraudulent case, and 0 class, the negative class, that's just kind of the standard. We're okay with this. And so only 0.172% of these are fraudulent cases. This is going to really impact how we make our machine learning model. It's going to be very different when we're looking at such an imbalanced data set where almost everything is the negative class, and we only have a couple of them that are the positive class. To get set up, we're going to want to go to our account setting in Kaggle, and I'm just going to jump to that because I'm purposely not showing some information. Under the API section is a create new API token. We'll want to do that. We may want to expire them if there's something that's left over, but most likely just want to create. That'll make a kaggle.json file on your computer. It'll download to that. Basically, you just need to go upload this to our Google Colab or whatever system you're going to want to be using. And I'm using Google Colab, so I uploaded it here, kaggle.json. Now this stuff shouldn't be here quite yet. I'll show you how to get that set up right now. So assuming we have kaggle.json uploaded here already, what we're going to do is first do !mkdir and then ~/.kaggle. That'll make a folder, and then what we need to do is copy this over. So we'll do copy kaggle.json, and then we'll move that into exactly where we just put that there, where we just made that folder. I am going to put a slash on the end here, and now we're going to change the permissions of the file. So this is chmod 600, and basically this exact location, so that's going to be this, and then slash this, okay? And then slash this right here. I'm going to do one more, which is Kaggle, and if Kaggle isn't here for some reason, you will have to pip install Kaggle, but it should be here, Kaggle datasets, download -d, and then we're going to type our dataset, which is mlg-ulb/credit card fraud. Then that'll have a zip folder that is going to be put on here, and after that we can unzip this, so we'll do unzip with credit card fraud.zip. And that's going to make a folder, put it in the right spot, change the permissions, download the dataset, get that as a zip folder, and then I actually have to specify that I want to replace this. You won't have to because you won't have done it yet, saying yes, and then it's going to have set up that we have creditcard.csv for you here. I'm going to choose to use pandas only and no PySpark, so what we're going to do is import pandas as PD, and then we'll set df equal to pd.readcsv with that file name, which is going to be creditcard.csv. And outputting df shows us our datasets. And I can close this now and see our data frame, which should have 284,807 rows as we saw. And let's take a look at what the columns are. The first column is some sort of time difference. Don't worry too much about it other than it's a value between 0 and infinity or so, a positive number. Then several columns, actually I believe 28 or 29 of them, V1 all the way up until V28, so 28, which are all values just between -3 and 3 or so. Basically, we don't think about what these actually represent. It's just some sort of information that transformed into this, and that's because the credit card companies can't show us this real data, because this is actually data that we cannot know what is the real information about these people. We also have something that's very interpretable, which is just the amount of the transaction. And finally, we have a class, which you can see it looks like it's all zeros, except if we actually go ahead and look, if we ask df subclass dot value counts, that's going to show us, as we saw before, 284,315 are zeros. They are not fraud, and 492 of the cases are fraud. A very, very imbalanced data set that's going to impact a lot how our machine learning models perform, or at least how we're going to train the models so that it can still perform well. A nice way to visualize the data set is with df.hist, and then we'll do bins is equal to, say, 30, and then what we'll do is fig size. This is very important, otherwise it looks absolutely terrible. Set fig size equal to the tuple of 30. After a little bit of time processing, because it's a lot of different images, we're going to have several different histograms. Now here's all the different columns histograms. So time, you can see it's a value between 0 and some big amount, and the rest of them are basically just skinny or slightly wider distributions that are roughly normally distributed around 0, and that's going to be the same for all of V1 to 28. Some of them are wider, some of them are skinnier, but mostly all the same. And then interestingly, we have amount over here, which is roughly almost all of them are some small amount, $20, $100, a couple $100. And most interestingly, we have class. As we saw, almost all of them are 0. It says 0.0, but really it's just 0 and 1. And then if you can even see it, there's a very, very tiny amount here that are 1s. Those are our frauds, and these are our non-frauds. So let's just do a df.describe here and summarize the data set. So I don't really care too much about all the pieces. Time has a minimum of 0, which makes sense to me. Maximum of a big value, that's fine. V1 to V28, sorry for the headache here. It's not really, any of these are important, so I don't really care about all of those. We have amount, which the average value is $88. The minimum amount is going to be 0, and the maximum is 25,000, which is a lot. And the class, as we saw, this value here, that's that 0.172% of them are the positive class. That's what that average can be represented as here, or interpreted as, and the values range from 0 to 1. Now we wish to do something called pre-processing or scaling our data. It basically means either changing the values between 0 and 1 or -3 and 3 or something like that. And so for the amount column, currently we have values between 0 and 25,000. We don't like that. So what we're going to do is with this one is something called robustly scaling. And that's because if we look at how the amount column is here, it's actually, there's big outliers here. So most of the data relies in this part, it relies in this part, except then there's some that are bigger values and it goes all the way, there's like one data point out here. And that's going to really mess up our scaling. So what we're going to do is something from sklearn. We're going to do from sklearn.preprocessing, we want to import something called robust scaler. And it's really easy to use this. We're just going to override the old amount column. So we'll do df sub amount is equal to, and actually I might as well just copy the old data frame in case we want it. So we'll do new df is equal to df.copy. So we'll grab that and then df sub amount, we'll actually do new df sub amount and set that equal to just the transformation of the amount column. So we do this with robust scaler, bracket, bracket, and then we fit the transform, so fit transform, and then what do we pass it? We'll pass it the old column, so that's going to be new df sub amount. And then not quite that, we just need to transform it to a numpy array, so dot to numpy, and then reshape it to be a two-dimensional numpy array, so -1, 1, so it's two-dimensional, and then after that, it'll fit the transform and make that the new column, so that if we ask what new df is, and actually let me just do new df sub amount, and then do a histogram, that'll make it the most obvious. So we see here, most of the values are between 0 and 25 or so. It's not quite as what we wanted. It's not 0 and 1 or between -3 and 3, but it's a lot better and it's not messed up due to the outliers. And in particular, if we do something new df sub amount, and then we will describe this just to look at what we did to it, we can see that the minimum value is now -0.3, the maximum value is 358, and we have a much smaller standard deviation. So we're pretty happy with this transformation. It's not just between 0 and 1 or -3. There's still an outlier over here way up there, but it's a lot better than it used to be, and this is going to help our machine learning algorithms a lot. Now, just for convenience sake, I'm going to get rid of that describe, and I'm also going to get rid of this histogram. So now we're going to do something to the time column. We're going to do new df sub time, and what kind of function or transformation do we want to apply to this? So let's take a look, and at the histogram we can see time. They're all values between 0 and 1, and there's no real outliers here. We're happy with something very common, which is just going to be standardization. Now we could easily import this from scikit-learn, but we're going to do it ourselves just to show you it's just some sort of transformation. It's going to be a lot easier on our typing if we do just time is equal to new df sub time to grab that in a variable. And then what we're going to do is this function, and don't worry too much about what I'm writing right now, I'll just explain what it does. We do time minus time, that's mine, time dot min, okay, and then we divide this whole column by time dot maximum, so the maximum value of that, and then we're going to actually subtract this by the time dot minimum. And so what this does, we can see now, if we output all of new df, we can see most of it's the same, except time column, we can see here each of these values is between 0 and 1. It's very, very clean. Now I'm going to split the data into train, test, and validation sets, and so to do this first, I'm going to just shuffle around the rows of the data set. So we'll do new df is equal to new df dot sample. where we set the fraction equal to be 1, meaning keep all the rows, and random state is equal to 1. Don't do random state is equal to 1 if you want to see slightly different results. This is just to make sure that you and I are going to see the same thing, and I'll see the same thing as I saw earlier. So new df is this shuffled rows where basically the same thing, but then mixed around. Now there's definitely other ways to do this, probably better, but this is totally fine by doing train, test, and val is equal to, we're just going to split it up. So we'll do new df sub, we'll say all of the rows until maybe 240,000. So the majority goes to training, and then we're going to split test and validation with the rest of it. So we'll do new df sub, what do we do? So 240,000 until about halfway. So that's going to be 262,000 roughly. And then the final one is just going to be new df sub from 262,000 onward. Now let's look at the value counts for each of these. So we'll do train sub class dot value counts, and I'm just going to copy that for each of them, but change it to test and validation. So this is going to be test, and this is going to be val. So this is the distribution of the classes where we have 240,000 in the training set are no frauds, 411 frauds, and in the validation we're going to have, this is validation, so 22,000 of no frauds and 36 frauds, and in the test set we're going to have 21,000 no frauds and 45 frauds. Now technically we should probably make sure that this is the same number as this, except it's not really too big of a deal. We're now just going to convert each of these into NumPy arrays, so we'll do train, test, and val is equal to train dot to NumPy, and we will do test dot to NumPy and val dot to NumPy, and we can output their shapes, train dot shape, test dot shape, val dot shape, and we can see their NumPy arrays that are basically the same shape as the pandas, except we can explicitly see here we have 31 columns for each of them. The first 30 are going to be for the predictor variables, the last one is going to be the output or the class. Now I'd actually rather that these say underscore NumPy because that's really what they represent, and therefore I can keep the train, test, and val as the pandas arrays, so I'm going to change that now. And that's the same, and I'm just going to rerun that again since we overwrote the variables earlier. Now I'm going to split each of these into input and outputs, and so we'll call that X for the input, that's going to be a matrix, so we'll do X train and Y train, and we'll do the same shortly for validation and test. But for train, it's going to be X train, Y train is train NumPy. Well, we want all the rows and we want all but the last column, and this is how we would do that, space colon -1. And for the other value, the Y train, this is the output. We only want the final column. That's what we're trying to predict. And so all of the rows and then just the final column. So no colon there, just like that. And we're going to just copy and paste this, but change it for validation and test. And I'm going to skip that because it's pretty boring. Okay, so just to make sure you understand what I did there, this is X train and Y train. X test and Y test is the same stuff, but coming from test. And X val and Y val is the same stuff, but coming from validation. Now I'm going to output the shape of everything here. And again, I'm going to skip that because it's pretty boring. So I opened the shape of everything. We can see for the training information here, we have an input matrix of 240,000 rows by 30 columns or predictor variables and 240,000 matching values or outputs or Ys. And the same thing, but for test and validation. Now we're ready to prepare a model. And so to do this, we're going to start with the most simple model there would be, which is going to be from sklearn.linear model. We're going to import a logistic regression model. And it's very easy to use, as all of them are actually, but it's especially easy for this one. Logistic model is equal to logistic regression, and then we just have to fit this thing. So logistic model dot fit, we give it the X train and the Y train, the input and the labels, and then what we do is score this thing. So we're going to get a better classification report is what we'll call it soon, but for now I'll just say score, which basically will assume it's an accuracy. So X train and Y train, here we get, it says it's not going to converge fully, but we can see it's a very high accuracy, so I really wouldn't worry about that message. Now here we can output a better classification report with from sklearn.metrics. We will import classification report. And so we'll print, we actually have to type print there, the classification report of, we have to give it the Y val. So we're going to do it on this on the validation. Remember, this was on the training set. We could have actually evaluated this on the validation as well, but we're going to do this on the validation for sure. Y val, comparing that to the logistic model.predict, its predictions given the X val. Okay, so comparing the actuals of the validation with the predictions given the input from the validation. So how good does it do on the validation data? And we also give it target names is equal to the classes 0 is going to be called not fraud. This is just for our purposes so we can read it a little better. better. This is the not fraud class. This is the fraud class. Now here's our classification report. We have many different terms here, and if you don't know them, that's totally okay. We're going to discuss that now. Now, you've probably heard of accuracy, which basically just means out of all of the examples that we saw, how many did we classify right? And that's not thinking about what class it was. We're just thinking about, okay, whatever it actually was, did we get it right? Well, we got close to 100% accuracy. That's what this says. And it claims 100%. We actually did not get 100%. If we did get 100%, that would be really, really good no matter what. But given that this is not 100% actually, we can see that because of these numbers here. And so we have very high numbers for not fraud and lower numbers for fraud. And let me explain why. In general, machine learning models get better and better at classifying given more data. And since we have so much more for not fraud than we do for fraud, that means it's going to be a lot better at classifying not fraud than it is fraud. In particular, we're actually going to be a lot more likely to predict that it's not fraud, just because that's so many times that we've seen that the model's going to start to assume that we're getting not fraud instead of even thinking about if there's fraud because of this imbalanced data set. And so what we see here is that it's really good at getting not fraud because the model's basically just assuming that it's not fraud, but we're actually not that terrible at predicting fraud since we see that these numbers are not zero, which they could have been. And let me explain what these numbers mean. Now, if we have a model that predicts whether something is not fraud or it is fraud, this gives rise to 4 possible scenarios. And by the way, we're going to start referring to fraud as the positive class and not fraud as the negative class. Okay, so in here, we could have this on the left here. This is what it actually was for any transaction, whether it was actually fraud or whether it was actually not fraud. And over here, this is what our model predicted. So we could guess that it was either fraud or it was not fraud for any possible transaction. Any of these 4 combinations are possible, and there's a term for each of them, which is very important. So when it was a positive and we predicted that it was a positive, well, okay, this means that we got it right. And so the first part, what I'm going to call it here, it's true. So it's true, whatever follows. And what follows, it's positive, okay? So this word was what our model predicted. We predicted positive, and it's true that it was a positive. As opposed to over here, when, well, it was fraud, when we predicted not fraud, and so that's false, we got it wrong, that it was a negative. So again, here, our model predicted negative, except it's false that it was a negative. It was actually a positive, but we predicted negative. And now also we could have that it wasn't a fraud, but we predicted fraud. Well, it's false that it was a positive, okay? It wasn't a positive. We predicted positive. It's false that it was a positive. It was actually a negative. And now here, finally, we could also have it wasn't a fraud, but we predicted that it wasn't a fraud. And so it's going to be true that it was a negative. We predicted that it was a negative, and that was true. So here again, we could have true positive. That means that we got it right in predicting that it was a positive. We could also get it wrong in predicting that it was a negative. So we guessed negative, except it was wrong. It was actually a positive. Or we could also have that we predicted that it was a positive, but we got that wrong. It was actually a negative. And here finally we could just get it right that it was a negative, and it was a negative. We predicted negative. Now we can talk about precision, recall, and soon after that F1 score. So just look at the fraud row right here. We want each of these values to be 1. That would be a lot better. And so 0.73, what this basically means, well, for precision, it's a measure of false positives. False positive, again, meaning it was false that it was a positive. We are predicting fraud when it was not fraud. Again, we are predicting fraud when it was not fraud. And so this is a transaction that a customer, just you and I was trying to use our Visa card or whatever, and our bank said that it was fraudulent, and so it didn't let us do the transaction. So how big a deal is that? Well, it's honestly up to, the bank or whoever wants to decide that, how big a deal it is when a customer is trying to make a transaction and we said it was fraud when it wasn't fraud. It's definitely irritating, but is it as bad as the opposite, which is false negatives? So recall is a measure of false negatives, which basically again says, well, it was predicted to be negative, but that was false. We predicted not fraud when it was fraud. Again, we predicted not fraud when it was fraud. So if it really was fraud and we predicted not fraud, well, that means that a fraudulent transaction got through. We let them do it. Our model didn't detect that, and we let them do it. So precision, the higher that means, okay, we're getting a lot better at not signaling when real people are doing legitimate transactions. We're actually not flagging that. And recall would be, well, we want that to be high because then a fraudulent person would actually get caught when they are doing fraudulent transactions. Now, the question you might be wondering here is, what is accuracy? Because we have 100% accuracy here. That means that of all of the examples that we saw, of all of the transactions, we got, say, 100% of them right. Well, actually, if that was really true, that this was actually 100% accuracy, then we would be very happy, because that means we got every single thing right. Except that's definitely not true. This precision and recall being less than 1 shows that we got something wrong. And so this is more like 99.999% accuracy, and that's still really, really bad. It's bad because of these fraud examples, it got a bunch of them wrong. And so the accuracy is very high because of this imbalanced data set. We have so many more not fraud examples than we do fraud. And so even if our model, all it did was ever just say every single example is not fraud, which is obviously wrong because there's fraud in the data set, and it's a totally useless model if it just assumes that it's not fraud. We would have a very high accuracy with that just because it would be right almost all the time. Like, most of them are not frauds, so we'd have a high accuracy. Except for the examples that are fraud, it's getting those wrong. And so that's why we can't just look at accuracy. We have to look at precision, recall, or F1 score, which is a combination of those. A high accuracy only is good if the set is balanced. So if we had 50% fraud examples and 50% not fraud examples, and we got a really high accuracy, well, that's great, because we must have done both on good on both of them. Except because the imbalance of the data set, it's even if it just predicted not fraud, we'd still have a high accuracy, and so that's not a good or even useful model. Now, no matter what here, our conclusion is that we're not happy with our model. So let's try something else. We'll do from TensorFlow, and so that means we're making a neural network. Let's make a shallow neural network, something just a little bit more complicated. We'll do from TensorFlow.keras.models. We'll import sequential. Okay, so make a sequential model, a shallow neural network, and we'll do from TensorFlow.keras.layers. We'll grab our layers, and we're going to get an input layer to start our network. That's not layer, that's wire. Layer. We're going to get a dense layer, and we might not need batch normalization, but often it's not a bad idea. We're also going to set something up for saving the model. So for TensorFlow.keras.callbacks, we're going to import model checkpoint, and we'll discuss that shortly, but it's just a way to save our model, only the best one that we want. So shallow network, okay, shallow NN is equal to sequential, and let's add layers to this thing. We're going to add an input layer, so shallow NN dot add input layer, and so we need to specify the shape of the data, and that is going to be train x. No, that's not right. It was x train. So x train dot shape sub 1. Okay, so that's the second part of that. That is, if we remind ourselves what x train is, it's rows by columns. Columns is the data, the variables that we're looking at, and so we want to look at 30 of those. I could have just typed 30, except if this were to change somehow, I'd rather it's just fixed like that. And we're going to put a comma there just to make Keras a little bit more happy. Okay, so now we're going to add some dense nodes. So we'll do shallow NN dot add dense, and it's pretty arbitrary here what we can do, but let's try just 2 ReLUs. Okay, not a very complicated network, just a little bit there in the hidden layer. So now what we'll do is add batch normalization. Probably don't need this, it would be fine, but what batch normalization does is it's going to help us basically just learn the data a little bit better. Okay, so we'll do that, and then we'll do shallow NN dot add with dense 1 and sigmoid. And we're adding a sigmoid. This means a value between 0 and 1. So this function we just made is going to take in the same information as above. It's going to take in a transaction of 30 different variables, and it's going to output a sigmoid, which is just a value between 0 and 1. We'll interpret this as a probability, specifically the probability of the transaction it received being the positive class or being fraud. And so if it outputs a 0.9, that means it has a 90% guarantee, or it's 90% confident that it was a fraud, and so we'd guess that it was a fraud. And if it was maybe 40%, well, that means it's actually more confident that it's not fraud, and so we would predict not fraud. It's based off that 0.5 mark, where if it's less than 0.5, we'd predict that it's not fraud, and higher than 0.5, we would predict fraud. And that's actually what the logistic regression model does as well, except usually when we predict it, it's actually going to know that beforehand, but it does behind the scenes output a probability, and they're converting that already to the class based on that probability. But here we're actually going to have to know that this really does just output a probability, and we'll have to make our own function to predict the class from that afterwards. Now we're going to set up our model checkpoint to save the model. So checkpoint is equal to model checkpoint, where we specify the name where we want to save this to. So this is going to end up saving to a folder called shallow.nn. We can load from that later if we ever want to. And we're going to do save best only is equal to true. And so as we can see, the monitor is the val loss. And so we only want to save the best one. We want to save the model that has the lowest validation loss or the highest validation accuracy. And yes, again, we just decided that accuracy wasn't a great measurement, but that's what Keras is going to force us to use here. So we'll save only the one with the highest accuracy on the validation set, and we'll fit it with that soon. First, we have to compile the model. So I'll do shallow.nn.compile. We're going to specify a couple things like the optimizer, which honestly the default would probably be fine, but I usually use the optimizer as Atom. I'm also going to set up that the loss, this is the most important thing here, is the binary cross entropy. Okay, so this is just a way of saying we're doing binary classification, and so this really does treat it as a probability. We want to maximize the probability. We also want to do metrics is equal to accuracy. And again, not an amazing measurement, but it's what we're going to use in the short term. So we're happy with that compiling and making the model. Now let's just make a summary so we can see that it outputted or it created what we wanted to create. We can see it first takes in 30. I don't know why it doesn't show the first layer, but it takes in 30. We then see it turns it into 2 nodes, and then it turns it into 1. So this is that probability at the end. We're now going to fit our model. So we'll do shallow.nn.fit, and we're going to pass the training data. So that is going to be xtrain and ytrain as the appropriate labels. We're also going to pass in the validation data like this. So validation data is equal to a tuple of the input and the output with xval and yval, and we're going to do epochs through the dataset is equal to 5. We'll do 5 runs through the dataset, and callbacks is equal to the checkpoint to make sure every time it does an epoch, it checks to see, do we want to save the model based off of, is the validation accuracy higher than it used to be? If yes, then we're going to save it. If the validation accuracy actually got worse over time, we don't want to save that. And so let's run that, and I will talk to you after it's done training. So it's done training, and the main conclusion that we get is that we supposedly fit the data very well because we have very high accuracy on the training set, and it generalized very well to get an accuracy very high in the validation set. Except, as we talked about, is accuracy really a good measurement? Well, let's take a little bit of time first preparing a prediction function, as we said before, changing that probability into a class, and then we'll check with the classification report again. Now, just to show you what it would predict if we didn't do anything to it at all, so we can adjust this, shallow.nn.predict, let's just give it the training data for fun. So this should output the labels that it thinks that each of them are. And what it does predict is actually something a little bit different. It gives the probability of each class. Okay, so we can see it's all very low that we see, which makes sense because in general, the model is going to predict that it's not fraud. There's so many not frauds in the dataset, it's very often going to predict not fraud. From this, we actually want to do something very, very small to it. We want to do flatten first, and that gets rid of that irritating list in the middle of it. We saw each of them was around a list, and we don't really want that. So this is what flatten will do. And that would have a shape of basically just however many examples were in the training set, and something like 240,000, I believe. So it'd be that. And then if we change this to greater than 0.5, well, it predicts, actually, I'm going to do just a little bit more, just to change it to an integer as well. That'll make it a little bit easier. We'll do that dot as type with an int, and what this does is, well, I can just show you that it's going to convert that probability into a class. Okay, so it predicted either 0 and 1 for each of them, and we don't see there's any 1s in there, but there's probably some in there. Now what we can do is turn this into a function because we are going to use this repeatedly. So I'm going to call this define neural net predictions. That's because whenever we make a neural net, it's always going to have the same type of output that looks like this. Maybe something different in the beginning of the middle, but it's going to have the same type of output. So we can do model, so we pass it some particular model, and then an input data that we want to give it. Okay, so we'll do that, and then what we're going to return, we'll return this thing, except actually, yeah, that's all we need our function to do. We're very happy with that. And then just to show you what it would do, we could do neural net predictions with shallow NN, we pass that model, and then we could also pass maybe the validation set. And it would output something that looks like this, which is exactly what we would want for a classification report, which we'll make. And we can't really tell a difference between this and what we just saw before, but that's really what it's doing. So just like before, we're going to print the classification report we're going to give it the validation output, and we're going to give it the predictions. So that's going to be the neural net predictions, basically exactly what we have above. There's shallow NN and then xval, so what we would predict for that. And then again, we're going to say target names is equal to the first one is not fraud, and that should be in a list. So sorry, we have a list there of not fraud and then fraud. And then after this classification report here, we should see invalid syntax. Let me fix that. Looks like it's just the other bracket there. And classification report, let's take a look. Okay, sorry, it just showed that I have an error here and I know exactly what it was. Inconsistent number of samples. And so in here, I called this X train when I actually just meant this as the X that I pass in there. That is calling the wrong thing. So there, I'll change that and we'll run that again. And yeah, it ran a lot faster that time. That makes sense. So here, if we call this again, we'll see a classification report, F1 of 0.7 and 0.64 precision, 0.78 recall. If we compare these numbers to above, let me just put them in a notes file that we have over here. I don't need that anymore. So this is going to be, I'm going to keep track of this. So this is shallow neural net on validation is these things, where the first one, this is going to be the precision, this is the recall, and this is the F1. Okay, so that's the shallow neural net on the validation. And here, the logistic regression model on the validation is these numbers. Okay, so let me just put that in there and here. That's going to be slightly messed up here. Logistic on val is fine. So here, our logistic regression model has a higher precision, it has a lower recall, and in general a lower F1 because that recall is a lot lower. So what are we happier with? Well, if we're going by F1, which is a balance between precision and recall, we're definitely happier with that shallow neural network. Maybe we did actually want precision more. Again, precision is talking about false positives. It's false that it was a positive. It's false that it was fraud, as in we predicted fraud when it was not fraud. We predicted fraud when it was not fraud. And so that is an issue because our customers, they're trying to actually buy stuff, but they can't because it was predicted to be fraud. And so this logistic regression model, it does a better job of that not happening. But it also does a lot worse a job. It's going to do a lot worse on when fraudulent people are making these transactions and they're actually going through because we're not catching them. So what do we care about? Well, we're definitely going to prefer the shallow neural network. I think most people would prefer that, but again, it's up to the business problem. Some people might actually prefer that higher precision. It's very, very easy to make different machine learning models, so let's just do a random forest for fun. So from sklearn.ensemble, it's an ensemble model, we'll import a random forest classifier, and then we'll make one with rf is equal to the random forest classifier with a max depth for the trees. Max depth is equal to 2, and njobs is equal to 1. That's going to help njobs equal 1. That's going to help the CPUs work on this. Sorry, -1, not 1. And then we're going to fit it with rf.fit. We'll give it xtrain and ytrain. And random forests take a little bit long to train. We'll see what happens, but it shouldn't take too long. And then after that, we're just going to print this new classification report on the random forest. So we'll do that, but not neural net predictions. That is instead going to be just with rf.predict with the X validation. Okay, give it that, and we'll see how this new random forest model did. Okay, let's add this to the list before we take a look at it. So we'll just say that this is the random forest. Random 4 on val is fine. And here is our output. So the highest precision so far with 0.81 is very high. The lowest recall, that doesn't surprise me too much that, if we get a huge boost in precision, we're actually going to get a worse output and recall. This makes sense. But again, we might be really, really happy with that high precision, even though it's a low recall. Or conversely, again, we might be really happy with this high recall and care less about the precision. But either way, I would definitely still go so far with the shallow neural network, which has a 0.7. Let's now try a gradient boosting model. So we'll do from sklearn.ensemble, we're going to import gradient boosting classifier, and then we'll do GBC for gradient boosting classifier is equal to, well, that thing, I don't really want to say that again, gradient boosting classifier, and I said it again, and with n estimators, is equal to 100 of them. It's going to be a big model to train. Actually, I don't want it to take that long, so let's just do 50 of those, and we'll also do set a learning rate, not a kerning rate, a learning rate equal to 1.0, and then with a max depth just equal to 1, with a random state is equal to 0. Okay, if you don't know how to customize those yourself, don't worry too much. I don't really know too much about the specific model either, but it might work. gbc.fit with xtrain and ytrain, and we are going to just copy and paste that classification report, and all we have to do is change rf to gbc, just like that. And this one will probably take a little bit of time, but I will see you when it reports. Now we have yet another model here with accuracies 0.67, 0.67, 0.67. So gradient, we'll just say booz val with these values, okay? So we can see compared to the shallow neural network, it has a slightly higher precision, and so it's actually the second highest in terms of F1 score. And so if I was just to rearrange these according to the F1, then we can see it looks like this. This is a good way, by the way, if you're ever making machine learning models, just to organize it like this based off of the metric you're most interested in. And so F1 highest with shallow neural network, and this one close behind, gradient boosting, it does have a higher precision, but quite a bit of drop off on the recall. So you again might take this model if you care more about the precision, but it's a pretty big drop in recall. The final machine learning model we're going to make here is called a support vector machine, and it's going to be just a linear one. So from sklearn.svm, we'll import linear svc, support vector classifier is the term, and so we'll say svc is equal to linear svc of, we can specify the class weight equal to balanced. And so what that says here is actually, no, keep in mind that there is much more not fraud examples than there are fraud examples. And so it's going to place a lot more weight when we do see a fraud example. It's going to have that impact the data a lot more than a not fraud is to try and balance this out. So we'll do that, and then we'll fit the model with svc.fit with xtrain and ytrain. And as usual, we're going to copy and paste our classification report, except changing this to svc, and let's see how that does. So here we have very good scores, 0.68, 0.78, and 0.73. Adding that here, we can see, I'll call this linear SVM on val, and this is 0.68, 0.78, 0.73. This is a new leader for a couple things. It is a new leader for F1, which I'm going to put at the top here. It is actually tied for the recall rating, so it's definitely the best model so far. It is not worse than anything other than, if you really care about precision, then you may want one of these other models, but I would definitely choose this linear SVM so far based on that awesome F1 and pretty good precision recall, unless you had a preference for precision. Now, if we were really happy with these, then sure, that's fine. We could take one of these as our model. We could look at the F1 and take linear SVM. We could look at the precision and take the random forest, or many different other options here. But what we're going to do is change the data set, okay? We still don't like this imbalance of the data set where we have so many more not fraud examples. You probably have thought, why can't we just take some of the not fraud examples out? Or why can't we just copy some of the fraud examples and put them in the data set to make the same number? No matter what, let's just make the same number of classes so that the support here is going to be the same for each class. And so the easiest thing that we could do is just called like downsample or undersample. Basically, just take away a bunch of the not frauds. Let's do that from the data set. Now, if we remind ourselves, we have new df, and we'll just do new df.head, is our big data frame with everything scaled appropriately, and this is going to have both class examples of 0 and 1 in there, frauds and not frauds. So that is new df. I'm going to get rid of that for now. That was just a reminder. And so let's split this into its frauds and not frauds. So we'll say frauds is equal to new df dot query, where the class is equal to 1. That is the frauds, and we can get not frauds, not frauds. Sorry about that. Not frauds is equal to this with classes 0, And let's just output the value count to each of these so we can see not frauds, so not frauds, subclass dot value counts, as well as the same thing for frauds. So that with frauds is going to show that we separated them. And so here we have 284,000 not frauds and we have 492 frauds. Now let's make a balanced data set where we drop a whole ton of these and have 492 frauds as well as 492 not frauds, dropping a ton of information. Let's see if it helps to balance the data set. So we'll do balanced df is equal to pd.concat, where we give it this list of data frames, and it's going to be the frauds. So we'll put that first, and then the not frauds, except would be all of them. We're going to sample this randomly. And how many do we want? We're going to put it the length of the not train. We're going to put it the length of frauds. Okay, so that's 492 of those. We're going to now, this is going to basically balance the data set, and we're going to do it randomly. We could probably just take the first 492. It wouldn't be all that different, but we're going to do this with balanced data frame is this and that, and we'll set the random state equal to 1 so we can see the same results every time. And that is balanced df. And we'll see if we do balanced df subclass dot value counts, we're going to see the following: 492 in each of them. I computed here for you 492 times 2 is 984, so that's how many values total are in this. Now we are going to just kind of rotate this around, and I don't really need that there. So we're going to flip the rows of this, randomize them like we did before, again with the random seed or state equal to 1. So what we're going to do is just balance df is equal to balanced df dot sample, sample with the frac is equal to 1, and the random state equal to 1 as well. So that will just show the whole balanced df right there is 984 rows by 31 columns, and it's shuffled pretty randomly where we can see classes of each are showed up. Now we're going to want to convert this into train tests and validation sets. To do this, I'm going to first convert the whole data frame into a NumPy array. So I'll just do balanced df NumPy is equal to balanced df dot to NumPy. Okay, and then after we have that as a variable, we'll do train x b for balanced, and train y b for balanced again is equal to balanced df. And what do we want here? Okay, so again, and I actually forgot, I think it's 984, so 492 times 2 is 984 values. Okay, so let's actually go give the first 700 to the training set, and we'll split the other 284 evenly over there. So what we'll do is up until 700, so balanced df, this is going to be to NumPy, or sorry, balanced df NumPy, all of them up until 700, and then we want all of the columns until the last one. We don't want the last one. And here we want the same thing, except we want only the last column. Okay, so that's good to go. We're going to do something fairly similar, but convert this into test. So this is going to be test, and then test. And what do we want to devote to this? I'll give it 700, and it's going to be, so difference between 794, or 984 and 700 is 284 values. Okay, so between that, we're going to do 142, so that this is 700 until 700 plus 142 is going to be 842 values, so that we can split the test and the validation set evenly. Okay, so we have that, and we'll do that just like that. And same thing over here is what we're going to devote to the testing information. And then we're going to do something pretty darn similar with the validation. We're going to make this actually train X. I think I was calling it X train before, so I'm going to just fix that up quickly. This is X train B, Y train B, X test B, Y test B, X val B, and Y val B. Okay, and down here what we're going to do is just 842 onward up until the last column, and 842 onward, just the last column. Okay, and I'm going to output the shape of everything to make sure that that worked out. And we can see 700 rows with 30 columns for the input train, and that matches up with 700 values. We have 142 and 30, 142, and 142 and 30, 142. Looks good to me. One thing I do want to do as well is just convert these into as type with integers because it makes our input just a little bit easier if it's not floating point values, but instead actual zeros and ones. I also want to look at the distribution or the number of classes that are in each of these things. So I'm going to turn them into pandas series for now and do y train. Okay, and we do that dot value counts, and I'll just show you for the first one what this is doing. We can see we have 240,000 devoted to that because that is very clearly the wrong thing. Y train B has 358 zeros and 342 ones, 358 not frauds, 342 frauds. So it's not perfectly evenly distributed, but it's really, really close. So that's good enough. We're also going to do the same for testing and validation. So I'll convert that to test and convert this to validation. And let's see in here. We have 358 and 342 is good, and these are a lot smaller values, but still close together, 74 and 68, 76 and 66. So remember, they're not exactly perfectly split because the way we just shuffled that data set and assumed, it's kind of going to be every other value is going to be switching, but it's pretty close. Now, we did the hard part earlier of making all of those machine learning models. We can just go ahead and copy all of that code, and I apologize for the headache of scrolling. If the scrolling's bugging you, please just skip to the parts where I'm actually showing the models, but I'll try to make it not too frustrating for you to see that if I have a logistic regression model right here, I will copy all of that code and scroll down. We have here a new logistic regression model, which all I'm going to ever do is just add B to it. For balanced, on the balanced dataset, it is the exact same model, but on different data, and it is just on this new data here. And again, for now, I'll score it. I will take that classification report shortly. And we got 0.96. Okay, so you see, it's a lower accuracy. This is an accuracy measurement. It better be a lower accuracy because it was so easy to get a good accuracy before with the way that the imbalanced data set was set up. I'm now going to grab that classification report, and I probably can just grab it from anywhere. It's not going to be too much different. I'll take it from this gradient boosting classifying one, and we'll see. Actually, I'm going to keep it on the same one every time. We don't really need that there. We're going to do the classification report with yval with b. Okay, I'm going to make sure that's copied again. So yb, we don't want that. We want it with logistic model b on the xval b. And let's see how that does. So we have a precision of 0.96, a recall of 0.84, and an F1 of 0.9. Okay, so a lot better here, but we clearly have a trade-off because for the not fraud here, our model's definitely not as good with these not frauds because of the way it was balanced and set up. Now, it's not going to be any better at getting the not frauds, so we're not going to see these ones here across the board with a great accuracy, but we will see that it's pretty darn good at getting both, but it's not perfect for sure. I am going to add this to a new part of the notebook, and I probably should be using Excel rather than this notebook file, but I'm totally happy with it. It seems to be working. So here we actually need to include both the not fraud and the fraud sections because before we were assuming that not fraud above here was just ones and perfect across the board, except this isn't going to be true anymore with these models. And so I'll just categorize this for you at the top here. This was on an imbalanced. Okay, these are imbalanced models, and here this is going to be a balanced section. And what is this model right here? This is going to be the logistic. Okay, logistic model gives this data, and we'll build this up. Now, for the purposes of saving time, I just copied all the shallow neural network code, except I appended _b wherever it made sense, so you can check for yourself that this makes sense if you want to. And I also changed epochs from 5 equal to 40 because the dataset is a lot smaller now, so an epoch or run through the dataset means a lot less than it used to, and so we're going to set that equal to a lot bigger value. We may actually run this again and see how it goes. So let's just run this, and I will talk to you after the 40 epochs right here. Okay, even on the 40th epoch, we still actually ended up writing because our validation loss continued to decrease. So I'm just going to copy this last line of fit code, and I will erase this output for now, and just show you at the end of another 40 epochs. Let's see what happens. Okay, and actually on the 16th epoch here, we saw the lowest validation loss we ever got, and that's the last time we wrote. So everything afterwards, we were just kind of starting to overfit and playing around with the training accuracy, and it wasn't really getting any better anywhere. So here we can actually see we are overfitting for sure. We have a 96% accuracy and an 89% accuracy on validation accuracy. So it's a lot higher on the training than it is validation. It is overfitting to the training set, so we'll see a drop off on its generalizability there. So this does mean our model was too complicated, and so I don't anticipate very good results from this shallow neural network, even though it's not very complicated at all, only 2 ReLU. We could actually even try switching this to 1 ReLU, but let's see how it performs before we touch this model at all. I'm going to grab that classification report, and we have to adjust this a little bit. So this is why val b is fine, except this is going to be, we'll change this to the neural net predictions, where again this takes a model first. The model we have to pass is the shallow NNB, and the data is xval b is fine, and yes, this will give the classification report, and actually it's pretty good. So let's take a look here. It looks pretty good. I forget exactly how the logistic regression model performed, but let's check this out. So here, this is the shallow NN. So we can see on not fraud, it's a higher precision. We can see it is a slightly lower recall on not fraud, but it's still pretty close. So I'm comparing this and this, and this and this, and this and this, this and this, this and this, this and this. And so basically, we have an F1 that's actually on average higher, so 0.9 for each of them is better. We do see, just different results. So really, I'd consider them pretty similar models, but the shallow neural network was definitely overfitting. So what I'm going to do now is actually label this as shallow NN 2 ReLU, but I'm going to make another model that's just the exact same thing, but only 1 ReLU, and I can show you exactly how I'll do that right here. I'm going to do this except shallow NNB. I'm going to call this just 1 at the end here. I will replace that with 1 to say I'm only going to add 1 ReLU in here instead of 2. That may help the model from overfitting a little bit. There's other things you could also do to stop overfitting, such as regularization, but I'm not going to worry too much about that in this video. We'll see if this makes the fix, and if it doesn't, then we're not going to carry on too much with this one. Okay, so the only other thing I think that's good here, no, I have to pass this, I have to write this over here, and then we'll fit that and see if that is what helps us out. Okay, so we actually wrote to it on the very last run again, so what we're going to do is just let this run for another 40. I'm going to cancel that, let it run in a new cell. Okay, and our last write there was on the 22, or on the 23rd epoch, so the last time we wrote to it. Again, we're still going to see an overfitting problem where we have 95 on the training and only 89 on the validation. I suspect the results here are going to be very, very similar, but let's see. So I'm just going to copy. This one will be very, very similar for the classification report. I'm going to put it in right here, and the only difference here is we'll pass that with B1. And let's compare the results. So here, let's take this information right there. It looks very similar, if not exactly the same. I can't tell a difference yet personally. Those all are exactly the same. Okay, so that did not help, and we may have to play around with regularization, but I'm not going to bother with that. Okay, and again, in the interest of saving time, I just copied and pasted with the underscore b's already fixed off screen. And if we train this model and show it on the validation data, well, we see something pretty interesting. We see, and if I was just to write this down as random forest, okay, I'll just write RF. So we'll just look here on fraud, a 1 precision and a 0.53 recall. Okay, so what this means, and it's only a 0.69 F1 score, which is really not that good, and 0.79 over here, so we're not super happy with that, but it's interesting because we haven't seen this before, in particular, a 1 precision for fraud here. So what this means, again, it's a measure of false positives where we have the positive class as fraud. So if it's false that it's positive, that means we're predicting that it is positive, except we are false about that. So we are predicting that it is fraud when it is not fraud. Okay, so we are never doing that. What this means here is that we are never ever predicting fraud when it is not fraud. As in, we didn't once annoy a customer. They were always going through, and we didn't once annoy them. But we definitely took a significant trade-off here because there were many times that we were wrong in other ways. Okay, so it's interesting to see. I don't really like this model in particular, but it's a nice result to see how different an outcome it can give. Here's the code for the gradient boosting classifier, and actually we can switch this to 100 estimators and maybe a max depth of 2 because we're probably allowed a little bit more room here. The data set's a lot smaller. And now what we'll do is check the classification report on this new model, and we can see, well, it's probably about the same, actually. It doesn't look too much different, so we'll call this gradient boosting classifier. And here's the data set, or here's the statistics on it. Well, it's pretty darn similar to the random forest, maybe just a little bit better in every scenario, so really not all of that useful. But again, it's interesting that we got that 1 in precision there. Okay, so finally we'll do the linear SVC or SVM model. I have the underscore B here already, and let's see that the results are again pretty interesting here. Actually, it's definitely better than the other ones. I'll just show you over here after I move it over. SVM has, okay, so F1s of higher for these for sure, so we're a big fan of that, and we have that 1 in precision. So honestly, people might take this model. I'll just compare it to the shallow network up here. So it's slightly worse F1 scores, but a big boost in precision. So if we did really care about that extra 6% or 4% in precision, then we may want this. Remember, this means that actually not once on the validation set did we ever say when a customer was making a real transaction, we never once flagged them off. But what we did do is we more times missed fraudulent transactions, and so that's probably not good. So what we'd probably do is take this model, and we can see for sure it's a way, way better than what we had before when we were not mixing or not balancing the data set properly. So that was huge to do that. And so we're going to take probably this shallow neural network model as our choice, is what I would choose, but it's really up to a business metric on whatever's most important. Maybe precision is, but probably take this shallow neural network. And what we do when we choose a model, by the way, hooray, we picked a model finally after doing all of this work, but it really, really is worth it. So I don't know where I'm going right now. This is not where I'm at. So I'm going to take any of these classification reports, and I'm going to make on the test set of information see how it does. So that's what we do at the end. We say, hey boss, this is how good our model actually is, and it's going to be with the neural net predictions. We're going to give that the shallow NN, and it's going to be with X test B. All right, and not predict, we don't need that piece. Okay, so right there, if we test it like this, we'll see that we have phenomenal scores across the board, even on the test set. Of course, it shouldn't be too much different from the validation set, and it really is just great. So here, tested, we'll just write tested neural net, and here's our scores. So it was, actually it's a fair amount different, but it's still relatively similar. We got some improvements on the not fraud there, comparing this. Let me just move this down so we can compare this really easily. We have this and that. So an improvement, and improvement. Actually, it just did better on the test set for whatever reason, which is really awesome. Higher F1 scores, so really, really happy to see. And there, we picked our model and we showed this is how good it is. So congratulations, this is a phenomenal project. Good job watching the video. It's a tough one, a lot of different things to see. Probably learned a lot, probably got confused a lot along the way, but that doesn't matter. There was a lot of pieces that we did learn, like precision and recall and F1, and to show there's so many different models, and it's not difficult to make those models on here. But most importantly, the takeaway is balance your data set and don't just look at accuracy. You can look at accuracy now, and that's fine because the data set's pretty balanced, and so accuracy means something. Except before, we really got to look at precision and recall when our data set is imbalanced, and you might just want to consider them no matter what, because that has a big impact on what the business problem actually is, what that means in real life. Precision and recall, or at least false positives and false negatives, they really do mean something. Okay, so congratulations. I really hope you enjoyed it. If you got this far, please, please, please drop a like on the video, put a lot of effort into it, and I'll see you in the next one.